X is allowed to take negative values, this inequality will not. So again, back to quicksort. So what does this imply for quicksort? Right. So what it means is we showed that if X is the running time of quicksort on an array of size n, we showed that expectation of X is something like n log n. And what Markov's inequality now tells us is that the probability that the running time is more than 10 times n log n is smaller than 1 by 10. So with pretty good probability it will always be less than, the running time will be less than 10 times n. So this is an immediate consequence of Markov's inequality. And last time we discussed this also a little bit about how to boost this further, right? Because what I have just concluded is that with probability 9/10, your running time will be smaller than 10 times n log. But what if I'm not happy with probability 9/10? What if I want probability of 99 by 100? What would you do? Okay, so
We just make T be 100.
yeah, so one way to do it is to say I make T be 100, in which case you will get that the probability that the running time is more than 100 times n log n is less than this. Right? But maybe this is an overkill. So this means that if you wanted 1,000, then you would have to make T be equal to 1,000. Right? But there's another way. Yeah.
Well, I think that this bound isn't really looking at the distribution a whole lot. Like, I think you could use more information from the distribution out of the running time probably to improve the bounds.
Right, so that is one thing you could do, but I'm asking, can you do something else which may seem a bit more hacky, but which gives a bound just using this inequality. Right, so last time, if you remember, we saw this repetition trick. Right, so what you could say is, I know that in one run of the algorithm, with probability, so suppose I declare a run to be a failure if my time exceeded 10 n log n. Okay? So then I declare this run to be a failure. Now if I do, and I know that the probability of succeeding is at least 9/10. So if I ran this 2 times independently, the probability of failing both times would be 1/10 times 1/10, which is 1/100. Okay? And probability of running, and the time you take is only 20 times n log n, as opposed to 100 times n log n. Okay? So this is a clean way to boost probability. Okay, so this is something that you should remember. Basically, you can always boost success probabilities by repetition. Okay, and very often you are faced with two things. You want a very high success probability. So one way to do it is to say what he just suggested, which is analyze it more carefully. But usually analyzing it more carefully takes a lot more effort. So what you would do instead is just get some constant probability of success and repeat independently. Okay, so that's a common trick we do. Okay. All right, so that's how we would increase success probability. All right, so today I wanted to talk about another common application. So I need this. I put this diagram. All right. So basically, so what I want to talk about is the question of hashing, which hopefully all of you have seen, and this is one of the basic algorithmic techniques, right? Like you have a bunch of things, you hash them to bins, and you do further computation. So, and abstractly, we think of hashing as the following process. So, suppose you have n balls that you are throwing in and n bits. Okay, so think of balls on one side, and you have bins on the other. And you think of independently hashing or placing each ball into a random bin. Okay, and do them one by one, and they are all independent of one. So where ball 2 goes is independent of where ball 1. Okay, that's what I mean by it. And so the kind of questions we want to understand are, given a bin, what is its expected size? So this is a natural question. You could also ask, what is the probability that a bin receives k different balls? So I give you a bin and say, what is the probability that this particular bin received k different balls? Okay, so that's one question you could ask. You could also ask things like, what is the expected number of bins that have 10 balls? So questions like this. And today we'll see how you would reason about questions of this kind. So there's another quantity I will talk about, which I put on the latest slide, but not in the first one, is the maximum size of the bin. The size of the largest bin. Yeah, because there will be some bins will, if you think about it, right, in expectation, you expect each one to have one ball, right, because n balls, n bins, everything is on average. So, I mean, everything is going uniformly at random. So, you expect each one to have one. Okay. But there will be a few bins that have more than one. There will be a few bins that have more than 10, for example. Right, so what would be your guess for what is the size of the largest bin? Do any of you have guesses? Have you seen it before?
Well, could we have used a terrible hashing algorithm so we have n balls in the same bin?
Well, that is true, but I'm saying that the algorithm is uniformly at random. So let's say I want. So this is a great point. What he's saying is, suppose you were super unlucky and all of them hashed to the same bin. Right? So then there's no bound you can give apart from n on the size of the maximum bin. But suppose I want an average, right? So suppose I want a confidence of, say, with confidence or probability at least 99 by 100. Suppose I want to make a statement with a reasonably high probability. So what would be the size of the largest bin? Have you seen this kind of calculation before? Okay, so we will do that today. Okay, so this is part of the kind of things we would like to see today. Okay, and these kind of things are useful because when you're thinking of hashing, right? So usually the size of the largest bin determines your worst case complexity of, let's say, searching for an item, right? Because usually you do a linear scan after you do a hash, right? And you expect that on average it will be 1, but there could be some bins that are overcrowded. Okay. And yeah, so we'll see what that is in a little bit. Okay. So let's start with the easiest question. What is the expected size of a bin? What is your guess of an answer for this? 1. And now let's see how you would formally prove it. Right? So how would you show that? Suppose I take a bin. So take, let's say, bin 1. Okay, so it's symmetric, so we can look at the first bin. So everything, the hash is completely independent. So let's just look at the first bin. And what is the expected size of the first bin? So let's denote by S1 the random variable. Okay, so that S1 is of beta. And I'm asking what is, for me, I'm just asking what is the expected size, what is the expected value of S? Right? And intuitively it's 1, but how would you formally say this? Yeah.
Wouldn't it be the sum of the probabilities of each ball at times 1?
So that is true, but why would that be the expected size? Remember, we defined the expectation in a slightly different way, right?
Yeah, wasn't it? I guess I thought it was like the probability of an event times the event.
Times what element, right? So if you use that definition, what you would get is sum over the whole range for the size of the bin. So the size of the bin can range between 0 and n. Okay? So you have j going from 0 to n of j times probability that S1 equals j. Okay? So this is how we define this thing. And if you think about it, you can compute this, of course, right? Because what is the probability that S1 equals j for some j? The probability that j different balls hash to this one element.
I think that's just the binomial probability, right? I can't remember what the formula is for that, but I think it's just the binomial, because it's a binomial distribution, it's you either include or you don't include the ball in S1.
Yeah.
And so it's essentially like I'm flipping coins with probability 1 over n times that it comes up heads, and then so you can kind of transform it that way to use that formula. I don't remember.
Yeah. So I mean, roughly speaking, you would guess that this has something to do with the binomial coefficients, right? So is that what you're going to say?
No,
Right.
I'm just going to say whatever.
No, but I was asking what is the probability that S1 equals j? So that means j different balls hash to S1. Right, okay, so what you guys are saying is that you look at the probability that one of them hashes to this, which is 1 by n. So the suggestion is, I guess, okay, so firstly, this is the expression, so we need to evaluate that one. So we are interested in this. And so we need to evaluate. And what they're saying is, if we knew the balls, suppose you wanted the first j ball, the probability of that would be 1 by n multiplied j times. Okay. So this is fine. Multiplied j times. But you don't know which of the j balls need to go to this n, right? Because all I'm asking you is what is the probability that the size of the first bin is j. So now what you can do is you can sum over all possible choices of which j guys you pick. Okay. So that's one way of doing this. So it turns out that this probability, you can think about this a little bit. Let me not spend too much time on it. This is exactly n choose j times 1 by n. Okay. So you choose which j balls you want to go into that bin, and that's n choose j of them. And once you choose them, it's 1 by n to the j. This is exactly what he said also. It's like you can view it as some kind of a binomial distribution. Okay, so this turns out to be the probability that S1 equals J. And this thing, and now you can plug it back into this equation 1. So plugging into 1, you get sum over J going from 0 to n, J times, I should write with a different color because these things are. Okay, sum over J going from 0 through n of J times n choose J. And if you're good at algebra, you can evaluate this and it will turn out to be 1. Okay, but as you can see, this is a mess, right? So you would want a slightly simpler way of doing this sort of a thing. And in fact, what he suggested initially seems like the right thing to do. I mean, you would want to just sum over the probabilities of each one going into this. I mean, you see, okay, ball 1 has a probability 1 by n of ending up in bin 1. Ball 2 has probability 1 by n. So the expected size of bin 1 is just the sum of these probabilities. That's what intuitively you would want to do. Right? So how would you formalize this kind of statement? And so it turns out the right way to formalize this is what is called the linearity of expectation. Okay? So what does this say? So let me write down the statement first. So the theorem is that let x1 and x2 be any random variable Okay, so if you don't, so formally I have to define what a probability space is and so on, but so I have defined random variables only informally, right? So we said that random variables are the outcomes of a random process, okay? So that's how we define random variables. And so think of x1 and x2 as two different outcomes of the same random process. Okay? So that's how we want to think of these things. And so these are two random variables defined on a probability space. Then expected value of x1 plus x2 equals expected value of x1 plus expected value. So this is why it's called linearity, because if you take the sum of these things, it splits out into the sum of the expectation. Okay. And this is actually a very powerful theorem. So this does not require x1 and x2 to be independent. Okay. So x1 and x2 could be arbitrary things that are just defined using the same probability, same random process. Okay. So and you still have this kind of thing. Okay. So if you wanted this kind of a thing with the product, then you need independence. Okay, so if you want product of random variables with product of expectations, that would hold only if those variables were independent. Okay, but the cool thing is that if you're just interested in the sum, it works no matter what. Okay, and actually I will show you an example. So in this case, computing the expectation by default was not that terrible. I mean, this is if you guys are used to this sort of calculation, this is actually not so bad. Okay, but I'll just show you an example where it's a mess to compute it exactly. Okay, so this is something that often helps. Okay, so how do we use linearity of expectation to do this computation faster or better? Any thoughts? So somewhere we want to bring up a sum of random variables. Right? So how would you write something like this as a sum of random?
Could you write it as, I guess I was trying to think if you could write it as an expectation of which, or the bin, I think if you could split it up and treat it as each ball is a separate random variable, but I don't know how it would work.
No, you're on the right track. So I guess the question is, how do you write S1, whose expectation you're interested in, as a sum of a bunch of random variables? S1 is the number of balls that were assigned to bin 1. Okay. So, what? Yeah.
Random variable ti. Okay, so you want it ball I. So
Okay, so a clean way of doing this would be to define a new random variable that let's define ti to be, this is a 0, 1 random variable. It is 1 if ball I goes to bin 1 and it's 0 otherwise. So now you have that S1 equals T1 plus T2 to T. Okay. And this is just an identity. Note that this is an identity that's always true, right? So it's an equation between random variables. And this is always true, no matter what the random process was. This is true. So that's how you think about these things. And now, so what is the expected value of Ti? Because this is now a much simpler random variable, right? So what is the expected value of each Ti? Again, you've got to use the definition. That's the only thing we know. And you've got to use, okay, so what are the different values that Ti takes? And, it's just 0 or 1. So what you would do is, you would say it is 0 times probability that Ti is 0 plus 1 times probability that Ti is 1. And this one is simply, this of course 0, and this one is the probability that Ti is 1, that is the probability that the ith ball goes to the first bin. So the ith ball has equal likelihood of going to all the bins. So this one is exactly 1 by n. This quantity is equal to 1 by n. So this shows that the expected value of this is 1 by n. And now this means that the expected value of S1 by linearity is just sum over I expected value of Ti, which is, there's n such terms. For each one, we just said that the expectation is 1 by n. So this is. Okay. So this is how you would do this calculation. And note that this is easier than playing with binomial coefficients, working out probabilities, and so on. Okay. And there are settings in which this can actually be quite powerful. Okay. So, but first, any questions on this? So, all right. Yeah. So this is something that. I guess if you guys have taken a probability class, then this is probably boring for you. But but this is something all of you should know. Alright, so here's a puzzle which some of you might have seen. So basically, suppose you have n numbered balls. So you have balls with numbers in them. So earlier we were just sitting in all balls were identical, right? So now think of numbered balls. Suppose you place them on a line from left to right. Okay? So this is like picking a permutation. So suppose I ask you what is the expected number of balls that are in the right position. By the right position, I mean ball I is in the right position if it's ith in the line. So suppose I ask you this question. So now if you went by the usual definition of expectation, right? So what would it be? It would be sum over I going from 0 to n, okay, of I times probability that precisely I balls are in the right position. Okay. And this, if you think about it, it's a little bit of a mess, right? So actually many of you would have seen, so this evaluating this probability could be tricky. Okay, so actually, yeah, I'm just curious, how many of you know what the answer would be for this term when I is 0? Do you remember a term for it? Like, what is the probability that if you have a random permutation, every element is out of order or is not in its right place? Okay, so this is usually called the number of derangements, and yeah, so it's like an arrangement in which nothing is in place or something like this. These are called derangements for some reason. And yeah, if you haven't seen it, it's fine. It's just curiosity. But all I wanted to say is that computing these probabilities can be a little messy. Okay? But in this case, if you use, if you try to write it as a sum of random variables, this problem becomes almost immediate. Okay, so how would you write the expected number of balls that are in the right position as a sum? So let's define a random variable x, which is number of balls in the right position. Now, how do you write x as a sum of random variables?
You kind of just do the same trick as before and just create n different random variables. One for is the first ball in the right place, if so, value 1, 0 else, and then the expectation would just be the sum over all of those random variables.
Okay, so you in this case you can just do what you did before. Okay, so you can just say let Ti be the random variable that is 1 if I is in position I and 0 otherwise. And now you can just say what is the expectation of x? This is equal to sum over I expected value of Pi. And this turns out, you can evaluate this. This is also turns out to be 1. So, because probability that I is in position I is exactly 1 by n, because it can be in any position. So the reason this turns out to be tricky to evaluate is, I mean, the TIs are not independent in this case. Okay? Because if I happen to be in position I, then nobody else could occupy position I. Okay? So everybody else has a slightly different choice. So the TIs are not independent. And this is what makes the problem a little bit tricky if you do it from scratch. Okay, and this is why this view of this problem makes it much nicer. Okay. So yeah, so the main difficulty for this basic approach is TIs are not independent. And we said that linearity of expectation holds even if things were not independent. Okay. So you just want these random variables that are defined on the same probability space. So yeah, so that's one. This is a very simple puzzle that illustrates when these things, when this trick simplifies calculations. Okay, so the model is viewing a random variable as sum of simpler variables can be used. Okay, so from the point of view of computing expectations. Right? So this is one of the main things for today. So let's look at the next couple of questions. Right, so we saw what is the expected size of a bin, that's one. And right, so now you can ask what is the probability that a given bin receives k balls? How would you answer this question? Like suppose I look at bin I, so I'm asking you what is the actually we just answered this I guess. What is the probability that, let's say S1 equals k? Okay, we just answered this, so I will remember what answer is. Yeah?
We use Markov inequality to say it is less than 1 by k.
Good point. That is my next slide. But first, what is the exact expression for this? So remember, we just computed this, right? So in order to tell you that this is a mess, we computed this, right? So if we have the probability that S1 equals some j, we said was 1 by n to the j times this n choose j. Okay, so yeah, so what you can, the way you compute it is okay, so this is something we just saw, right? You have to pick some k balls that have to go into this first bin. That can be done in n choose k ways. And once you do that, the probability that all of them go to that bin is 1 by n multiplied k times. Okay. And these events are independent because each time, somebody should have corrected me because there should also be this 1 minus 1 by n to n minus k. Okay. So nobody else should have gone because only then those events become independent. This would be an upper bound, but yeah, in principle, you want nobody else to go to this. Okay, so that's what makes all these events disjoint. So you want these k guys to go to this first. Nobody else should go. So all right. So this is the problem. Maybe I should go back and correct this also. So this is. Okay, so yeah. All right. So this is what we have here, and now you've got to ask. Actually, is this clear to everybody? The reason we got this expression. We are saying, look at, so when could it happen that the bin 1 receives exactly k balls, right? So the way it would happen is some k of these, of the n balls, all need to go to this bin. and nobody else needs to go to this bit. Yes, everybody else must go into this one of these other bits. So the probability that after you select these k balls, the probability that they all go to this bin is 1 by n to the k. The probability that nobody else goes into this first bin is something like this, is the second term. And the number of choices for these k balls is n choose k. So that's why you have the product. So this is so this is the probability of this. And now you've got to ask yourself. So now I'm coming to the question that he asked. Okay, so this is whatever it is, right? So it is some messy expression in terms of n and k. Yeah.
How is that what? How is this a binomial? Having more time understanding because we only have a limited number of calls. So
Yes, that's why it's a binomial, right? So it's like you have from the point of view of one bit. Okay, so this is like a binomial distribution in which you have n trials, and the probability of coming up heads is 1 by n. Right? Because from the point of view of this one bit, right, it's like there are n different balls that are turned up. Each one becomes heads with probability 1 by n. And if it becomes heads, it comes to this way. Otherwise, it goes to it.
but after one trial is the next one effective
No. I mean, that's how you define a binomial trial. Right? You have n different things, and they're all independent. The point is that they're all independent. So in the previous example, they were not independent, but in our original model when setting, the second ball has the same likelihood of happening. Right, so that's an important point. That they're all okay. So this expression, let me just write it as n choose k, 1 by n to the k. Okay. Yeah, if you're very careful about this, you could write this as n choose k times 1 minus 1 by n to the n times something like 1 by n minus 1 to the k. Okay, so, I mean, I don't think this is very crucial, but this is one way to look at this, because this thing turns out to be a constant usually. Okay, so if you really want, you can think of it like this, but the point I would like to make, even if you ignore this term, so you can say that this thing is upper bounded by n choose k times 1 by n to the k. So this is the first bound I had. Okay, so this is at most this. And this, for those of you who know, so this actually, this is less than or equal to 1 by k factor. And the reason for this is, actually, yeah, can someone say why this is? Why is n choose k divided times n? I mean, or you just have to know what this expression is. That's it. So
n factorial over n minus k factorial times k.
yeah, so this expression is n choose k is this, right? So n minus k factorial times k factorial, which if you expand it out is like n times n minus 1 times, you have k different terms here, okay, divided by k factorial. The point is that each of those k terms is less than n, okay? And you had a 1 by n to the k here, so it would cancel out each of them. So this thing would be less than or equal to 1 by k factor. This is, you didn't follow this, this is straightforward, you can work it out after you go back. Okay, so it turns out the probability that S1 equals K is smaller than 1 by K factor. Now you've got to ask yourself, what would I have got if I used Markov, right? So I know that the expected size of S1 was 1. Okay, this is what we saw earlier. And now if I use Markov, the probability that S1 is more than K would be less than 1 by K. And in particular, the probability that's equal to K is also less than equal to 1. It's K and O, right? So that's what this means. So, but this is only, but Markov's inequality only gives something like 1 by K, while what you get by a more intricate calculation is like 1 by K factorial, which is very, very tiny. Like if K is 10 or something, then 1 by 10 is a decent probability, but 1 by 10 factorial is minute. So this is so there's a big difference between Markov and what you get by a more careful calculation. So that's something you've got to notice. Okay, so the model here is Markov can be very big. Yeah, I will just say is usually very big. So that's just something that I wanted to contrast. But yeah, so this is a boundary value. And now you can ask yourself, what is the expected number of bins of a particular size? Like let's say size equals 10. How would you compute this? So the reason I'm doing so many examples is because I want you to get the message that if I want to compute the expectation of anything that looks complicated, I want to break it up into a sum of expectations. So how would you break it? Yeah.
Can we use the equations we had before of what's the probability that equals K, in this case 10, and sum it up across all the bins, so like 10 times that probability.
Right. And formally, how would you write it?
So I do the sum of the expected value of Si equals 10 times.
Yeah. So I guess what he's saying is, suppose you have X is your random variable of interest, which is number of bins of a certain number of bins of size 10. And then what you're saying is define S. Let's not do S again. Let's use P because that's what we're using. The Pi is the random variable that is 1 if bin I has size 10. 0 otherwise. So this is like an indicator. So these 0, 1 variables are often called indicator random variables. Okay, so it's something you know. And so this Pi indicates if bin I is of size 10 or not. So the number of bins of size 10, so X is always equal to T1 plus T2 plus T. And now all you have to do is the expected value of X is sum over I. And this, like you were saying, is this is sum over I. So firstly, it's equal for all I. So let me just write it as n times this. So for every I, this expectation works out to be the same thing because of symmetry. So this is n times. This is 0 times the probability that it's 0. 1 times probability that Pi equals 1. And what is probability of Ti being equal to 1? What does Ti equal to 1 mean? Sorry? No, I'm just asking, what does Ti equals 1 mean? By the definition.
I have size 10.
Yeah, so bin I has size 10, right? And this we just computed the probability. So we just said what is the probability that a bin has a particular size k? And we said that this is equal to this term, where the top term, where k equals 10. So that's something you can write down. And so this one equals n times n equals 10 1 by So this may not be particularly meaningful for you, but we have just seen that this is, at least you know that this is less than or equal to, this part was less than 1 by 10 factorial. That's what we saw. So this we know is less than or equal to n by 10. Okay. But what I would like you to understand is that this, until this point, this is actually an equality. Okay. So what this is saying is that, and in fact, this approximation turns out to be not very bad. Okay. So if so, this is actually approximately equal to this, and what this means is that there are actually a reasonable number of bins in the limit of like n being huge, right? Like n is significantly more than 10 factorial. There are actually enough number of bins that actually have size 10. Okay, so this may be a little surprising to you because you expect all the bins to be of size constant or 1 or 2 or something like that. The expectation was 1. Okay, but there are actually constant fraction. It's a tiny constant fraction. There are constant fraction of bins that have size 10. So that is something that you should know about these processes. Okay. So this is why hashing occasionally results in a long time for you to because there are actually cases for this. So alright. And now you could ask yourself, what is the size of the largest bin? Right? So this is again somebody had pointed out. Worst case, this can be 1 by this can be n. Right? So worst case, this can be n because you can be terribly unlucky. And all the balls could fall into the same bin, and that happens with like 1 by n to the n probability. Okay, but that's a very small probability. But suppose we are interested in having a statement that holds with probability 99 by 100. Then we want to ask, what is the size? I mean, yeah, what would be a decent bound on the size of the largest bin that holds with probability, let's say 99 by 100. So how would we answer a question like this?
What would the probability of the opposite of the probability that each one is below that amount?
Right, so you could start by saying, okay, so let's try to see what is the probability that this maximum bin has a size that is more than a certain k, right? Like, and you're saying, I could try to see what is the probability that all the bins have size smaller than equal to k, right? So yeah, so it turns out that this is the right idea. Okay, so the question you've got to ask yourself is, it's the negation of what this is what he's saying, but negation of what he said is this quantity. Okay, so it is, what is the probability that there is some bin that has k balls? Okay, because if there is some bin that has k balls in it, then there's then the maximum is at least k. Okay, and we want, and if you can bound the probability of this to be less than 100, 1 by 100. Suppose I find a k for which the probability that there exists a bin with k balls is less than 100, 1 by 100. So then it means that with probability 99 by 100, no bin has more than k ball. Okay. So this would be how we would formalize this question of what is the largest. So let me pause here for a second and see if, because in these probability things it's right to understand what exactly we are trying to say. So somebody has a question. If it sounds confusing, you should think of concrete values for k. Okay, so for instance, you can start saying, remember we said worst case this can be n. Right? Suppose I told you, okay, what is the probability that there exists a bin that has root n? Would you think this is likely? Why do you say it's somewhat likely?
Root n is not a very large number compared to n. We just saw that having a size 10 bit is pretty unlikely.
Okay, so this could be one intuition, right? So you could say that having a bin of size 10 was reasonably likely. It was something. It was a constant, and you could say, okay, maybe even the root n size bin is possible. Think of some number like this. Alright, so now, but how would you answer this question? What is the probability that there exists a bin with k balls? I guess there is one new phrase here that we haven't seen so far. It was the probability that there exists, right? So this never showed up. So far, we've just defined some random variables and played with them. But now we are actually asking, okay, you want some bin that is big. Not quite, I fix a bin and ask you what the size of that is. So it turns out, so let me write this down in a different way, which then makes sense. Okay, so one way to formally write this is you can say that this is probability that bin 1 has size k, or actually, is everyone familiar with this symbol for OR? Yeah, it's a Boolean OR. So OR bin 2 has size k, or so on. Bin n size bigger. So I've written this as an OR of a bunch of events. And each one is of the kind we've seen before. Yeah.
So I was going to say, I think you can just use the approximation for like a bunch of unions in the case that probably the union now with the one has K, the two has K, and so on and so forth. So you can just kind of take the earlier expression for any particular bin having K balls and sum them all up for each bin, that ends up being n times the earlier expression for the probability one bin has K balls. And that's going to be, its approximation, I think it's less than or equal to that value since they're not technically independent.
Okay, so yeah, so he summarized what my next slide says. So let me go to my next slide. Okay, so there is a very general. I mean, I guess the question is, so the important thing about this slide, which you should understand, is we wrote down the probability that there exists a bin as an OR of a bunch of probabilities. Right? So each one is an event. Okay, so this is the event that bin 1 has size more like this, event that bin 2. And we wrote the event that we are interested in, which is there exists a bin with K balls as an OR of these things. And once you do that, if you have any probability as an OR of a bunch of things, you can use what is called the union bound. So if you have a bunch of events, let's call them E1, E2 up to En. So an event in a probability space is intuitively what you expect it to be, right? So it is it either happens or it doesn't. It happens with a certain probability, okay, and it happens for certain choices of your random coin toss. Okay, so that's an event in a probability space. And what we are interested in is one of these events happen. Okay, so maybe I should have had this symbol here. Usually you think of events as sets, so it's like right? But yeah, so the probability that one of these things happens is less than or equal to the sum of the probabilities. And intuitively this makes sense, right? So because you are asking, you have, so I don't know how comfortable you are thinking about probability spaces, but you can think of like different choices for your coin tosses, and for some of them E1 happens, for some others E2 happens, and so on. Then this becomes exactly equivalent to the size of the union being less than equal to the sum of the sizes of a bunch of sets. And this is a basic fact in set theory, right? Like if you have a bunch of sets, their size of their union, it would be equal if these were disjoint sets. Otherwise, the size of their union would only be smaller than the sum of the sizes. So, so this is something which is again basic probability. So if you understand it, it's great. Otherwise, you can just take this as a known fact. Okay, so it's like saying if you have a bunch of events, then the probability that the OR of these events, just like saying at least one of them happens, is at most the sum of the probabilities of these things. Okay. So, alright. So this is what is called the union bound, and this is another very basic result in computing probabilities. Okay. So you want to compute the probability of something, you usually upper bound it by this. And this is again like the Markov's inequality. This is not always tight. Okay, so there are cases where the sum of these things could be quite large, and but still these things happen. Okay? But still one of them is bound to happen. And this often happens when, for instance, these EIs are independent. If EIs are independent, then actually this will be one of your homeworks, so you will see when that shows up. Okay, so if EIs are independent, you can get much better bounds. So than this. Alright, but for now we will just use this very weak bound. That probability of one of them happens is at most the sum of all of them. And now you can plug this into this expression. And now you get that this is less than or equal to probability that bin 1 has size at least k, bin 2 size at least k, and so on. So this is let's say to the n times probability that bin I has size. Okay. And now what did we see about this probability? We saw that this probability, actually, yeah, so this probability, we saw that this is less than or equal to 1 by k factorial. So this is, if you remember, something that we did over here. So you should be asking me, there it was exactly k, now we are at least k. But what you will realize is that if you sum 1 by k factorial plus 1 by k plus 1 factorial and so on, the leading term dominates. It's almost 1 by k factorial. Okay, so in principle that is right, but yeah, but you can still bound this by roughly 1 by k factorial. Okay, so let's not go there. So you get that this term is this. So let me actually write the whole thing, and then we have it. Okay. So let me summarize what we were here. So using the union bound, we get the following: that the probability that there exists a bin of size k is smaller than or equal to n divided by 2. Okay. And now the question is, when can you make this quantity less than 1 by 100? So the question is, for what k does this become less than 1 by 100? Right, so any thoughts? When does, for what k does, how well do you know your factorials? So yeah, I'm guessing that people have forgotten the approximation for factorial or have not seen it before. So there is something called Stirling's approximation, and so this is a very standard approximation for factorial. What it says is that k factorial is asymptotically, it is up to constants. It is k by e to the power of k, where e is the base for the natural log, like 2.718 constant. Okay? So this turns out to be a it's a well-known fact. It's called Stirling's approximation to the factorial. So if you use this, you will and you plug it back into this expression, you get that that for k equals something by log n, something like log n divided by log n. Okay, maybe with a constant like 10 or something, this becomes so this expression n by k factorial becomes less than 100 when k is something like this. So this is if you use Stirling's approximation. So this calculation is not that important, but what is important is the message here. Okay, so what is important is that when you have k being roughly log n, okay, k is like log n divided by log n, then you have that the probability that there exists a bin of size more than k is really tiny. So this means that when you do this kind of a random n balls into n bins process, the largest bin has size something like log n by log n with a very high probability. Okay? So for instance, there would be no bins of size root n, okay? Because log n by log n is much smaller. And this is almost tight also. Okay? So this is something you should know, that when you do this kind of random hashing processes, there will be a few bins that are of size log n by log n. And in practice, sometimes these could take a long time. So you might be unlucky and hit a bucket that hit a bin that has a long, something like log n, many numbers. So this is why people have come up with like better hashing strategies, because the uniformly random one has a small number of bins, but they have roughly log n many elements. Okay. So that's the thing. But I wanted to summarize. Okay, so today we saw a bunch of important things. That's why I have a summary slide. Which is the first thing we saw is this notion of random variables as sums of simple random variables. Okay, so if you want to compute the expectation and it looks messy to compute the probability, try viewing whatever you have as a sum of simple random. So that's one of the main messages we saw today. Other thing is, linearity of expectation, which is just that you have a bunch of random variables. The expectation of their sum is the sum of the expectation. And this is, we use that to use the first thing. And the other thing we saw is that Markov's inequality is not usually tight. And this we saw with this example of 1 by k factorial is 1 by k. Right? So this is not usually tight. We will see more examples in the next. In the next class, we'll see how you can get better inequalities than Markov. Okay? But at some level, what they will involve is applying Markov's inequalities to something slightly different. Okay? So that's that. And then we also saw this union bound, which is if you are interested in one of a bunch of events happening, you usually bound that probability by the sum of the probabilities of each of those. And so let's talk. Apparently, there's a plenary lecture of sorts going on now. So there's this AI speaker. You might want to go to that. It's at 12, so it's right after.